myself. So this is my four main posts. So position in UTM, in FKE. Actually, I'm a associate professor, and then in EVAT, I'm working as quality manager and also doing some research to become a fellow in EVAT, Institute of High Voltage and High Current. And I also apply some of my knowledge in industries, become principal consultant for global technical solutions. So this GTS is a Australian company, and their subsidiaries, they appoint me as technical advisors. So sometimes I went to sites and then do lots of high voltage testings for them, and then contribute something to the companies, and then bring some income, generate some income for UTM as well. So lecturer is not only teaching. So lecturer, we also need to generate income. So that's why I went to industries and then do lots of work as well. So maybe sometime will be quite busy, and then that's why I put this slide lah, so that you all understand, because I got some position in industries. Sometime I may postpone class. Okay, so hopefully it's not. Right, it depend on the demand from the industries, whether they have some projects that I need to deliver, right? So if don't have, then hopefully it's not lah. Okay, so that we don't need to postpone the class. So if I have, then nothing I can do lah. Okay, all right. So all right, okay, all right. So let's see what's the introductions for the high voltage technology. So before we move very detailed, especially on the concept, everything, the mechanisms, the breakdown mechanisms, the over voltages, the lightning, everything. So let's see what is the high voltage technology. Okay. All right. Okay. So before we move forward, so this is already confirmed. So test 1 will be chapter 1 and 2, electric field, and also the breakdown of gas. So will be on 23rd April 2025. This is on Wednesday. So the venue is on at P16 exam hall, level 2. So 5 o'clock in the evening. And then test 2, chapter 3 and chapter 4 on 11 June 2025. This was on Wednesday. And P15 exam hall as well, also 5 o'clock in the evening. Okay. So hopefully you all already got all this information lah. And then we have 2 quizzes on chapter 5. So I will take attendance as well. So why I take attendance? So this attendance is to top up. Okay. So hopefully your quizzes will be full mark lah. Okay. But if you attend in full, then I will top up based on your attendance. So let's say you don't get a full mark for your quizzes, then attendance will be we top up the marks lah. Okay. So we got 2 quizzes. So this I call level 1 and level 2. So level 1 is a beginner, level 2 is advanced. So this will be notified maybe on June 2035. So the quizzes will be online in e-learning, and the project will be chapter 1 until chapter 3, 1 to 3. And so basically I will inform this in e-learning. Okay, the group members, what are your the assignment instructions, everything, and then the submission link will be in the e-learning lah. Okay, just submit through the e-learning. So the submission of course will be on July lah. Okay, but I will try my best to give to you latest by next week lah. Okay, so I will, because I need to assign the group members in the e-learning. Alright? Okay, but don't worry, you still got lots of times. Boleh raya dulu, and then Julai nanti lah baru you all need to submit. Okay? Alright, so let's see some of the contents for this introduction to the high voltage technology. So firstly, we start with
Assalamualaikum and
definitions
very good morning to
according
everyone.
to the IC standard.
So can you
And
all hear
then,
my voice? Loud and clear, right?
Yes, Doctor.
Right. Okay. Thank you very much. Okay. So participants around 34. Out of 58. All right. Okay. No problem.
Doctor,
Yes.
sorry, but the QR code is invalid.
Oh, still invalid. Okay. So let me check because this one I took around 3 o'clock just now in the morning. So let me check again. Don't know what happened to this UTM portal. So let me check again. All right. 8 o'clock in the morning. Can section 3 scan first?
Doctor, the QR can use already.
Right now. Now I can get it. Okay. So let me get for session 4. Okay. Right. Right. Okay. Oops, sorry. Okay, this is for session 4. Let me make it smaller. Then let me check session 4. Yeah, I got it. Chris Ng, No Ashikin. What happened? Something went wrong. We apologize for inconvenience. So session 4 can scan, is it?
Yeah, can.
Right, okay. So I just wait maybe 1-2 minutes to complete this attendance before we move forward lah. Any one of you staying in UTM now? Or no one? Everyone already in hometown? No one, eh? Alright, okay. So let me check in the website. But now it's not reachable. Sorry, I saw chat just now. Okay, Aiman, hometown. Alright. Kat mana Aiman, hometown? Hometown kat mana? Johor bukan? Oh, Kedah. A lot stuck. Okay. Alright, still counting 26 for section 4. Section 3. Twenty-six over 27. Okay, right. So I think we can start lah. Alright, okay. First of all, thank you very much for attending the class today. So I know it's quite difficult to start at 8 o'clock. It's really quite early in the morning, quite early, but this is common, okay? But actually for this subject, lots of theoretical, and the class is start at 8 o'clock. So then it become like a Panadol, a medicine for us to get sleep. Okay. All right. So I try my best to convey some information because most of the slides that I prepared for this chapter, most of my slides are different from the other sessions, but the main idea will be the same from session 1 and from session 2. But I'll try to put some photos and some examples that are related to the industries. So hopefully we can experience something, right? Okay, let's see what of this chapter. Alright, okay. So this chapter is actually related to electric field study and also how we control the stress. Okay, so you can imagine that we discussed last week about some application of high voltage, and then you have seen, I think, some videos about the failures. Okay, so mostly the failures is due to the failure of controlling the stress. Okay, because the voltage is producing like electric fields. Okay, electric field is giving a stress. Okay, so in other words, we call as field strength. How strong is the electric fields in order to cause a failure? Okay, so in a high voltage, we have two main things. So the first is the insulations. So insulation have three media, right? So the first is air or gas. All right. So either we are using natural air or gas, something like sulfur and sulfuride gas or vacuum condition. We have oil, which is a liquid, something like using in transformer to insulate the active part, the windings and the core. And also we have like solid insulations. Okay, something like in cable, cross-linked polyethylene, EPR, ethylene propylene rubber. Okay, so or we can see also in the transformer they are using something like a paper, right? And also the resin is used in the stator winding for generator and also for the motor lah. So this is the types of the insulations. Alright, and then we have also another active components that we call as conductor. Okay, so conductor is made by something like copper or aluminiums, or it can made by steel, stainless steel, or anything that conduct the current. Okay, so in high voltage engineering, so as high voltage engineer, okay, if you are either you're design engineer or you're testing engineer, right? So you need to ensure that these two components, these two element, insulation and conductor, they are not touching each other. Okay, because we know that conductor is used to conduct the current, and So because the conductor should be isolated, okay, from reaching another conductor that is called as ground. Okay, so ground is zero potential, 0 volt. Conductor can be any voltage, but of course we have learned last week we have different voltage levels. We have low voltage, we have medium voltage, we have high voltage, extra high voltage, ultra high voltage. So all these voltage level have different values, and that's why they produce some stresses. They produce electric fields. And of course, this conductor will carry the current, okay? Because we learned last week, starting from generator that generate electricity, of course, in terms of power, voltage, and currents, then this power need to be transmitted to the consumers because consumer require this kind of power, okay? So this is called loads, right? So because we have these two elements, these two components, conductor and the insulations, so we need to control it, okay, so that the conductor may not reach the ground. So in between the conductor and ground, this is called electrodes. We have two electrodes, okay, so it can be made by any metallic components or metallic elements, and these two electrodes must be isolated or must be insulated by these three elements, okay, either gas or air or solid or oil, okay, or liquid. So we have these three media that is called insulation media, okay. So because of these three materials, so they have different properties. So the main properties that we need to consider in this chapter is called dielectric strength, okay, or we call electric strength, okay, electric strength, or we call as breakdown strength, okay. So because this insulation, they have properties, okay. These main properties is that how strong these materials to resist or to withstand over the stress or the electric fields forces that exerted on their media or on their atoms or their molecules, okay. So air, liquid, gas or liquid or solids, they have different dielectric strength or different electric strength or different breakdown strength. So this is the same thing, but I will always use this electric strength, okay. All right. So let's say we have a cable. This is a conductor and insulated by insulating media. So especially like SLP, cross-linked polyethylene. So this is polymer, a solid material. And this is the conductor. It's made by copper, right? And we have something like a semiconductor screen, or we call as conductor screen. And this is SLP to insulate this conductor, and this insulator SLP will be they have something like that they call as insulator screen. Okay, so this is like semiconductor layer. Okay, something they are using like carbon black, right? So but this is it's a semiconductor layer. Okay, or they call as insulator screen. Okay, so this is to linearize the electric fields, and basically the the insulator screen will be grounded, so they have their sheets. Okay, this is a grounding, and the copper will be at any potentials, any voltage, right? And then, so this kind of solid insulations is used to insulate or to isolate between the positive electrodes, okay, or potentials electrodes, and the ground potentials, okay. So that's why the insulation is used. So it's depend on their thickness. So the higher voltage, if the voltage is higher, then of course it can be a thicker lah. So higher voltage, so the thickness will be higher lah. I mean the thickness of or the diameter of the SLP, the insulations. Okay. So because of the conductor will carry the current and also potentials, and it has a different configuration, different shapes. So like this is like coaxial, okay, coaxial shapes. Now you can see we have like cylindrical insulator and also cylindrical conductor. So then it might have different electric fields, different stress, different forces. Okay, so then the SLP should have a better electric strength in order to withstand the stress coming out from this voltage. Okay, let's say like medium voltage cable, we are using 11 kV, the potential or the voltage, and yeah, the diameter might be in the range of 1.5 to 2.5 millimeters, right? In order to withstand the electric field between 4 to 5 kV per millimeter. Okay, so the higher the voltage, the electric field will be higher lah. Okay, we are going to see how we derive the equations. All right, for electrical engineers, we understood that the electric fields, so this is called field strength, okay, should be less than electric strength. Okay, so in order to prevent any failures or any premature failure, something like partial discharge, right? To prevent any sparking or arcing that may happen due to non-uniform electric fields. So the designer or if you are working for cable manufacturer, in the case for this cable, you should design your field strength. So field strength is depend on the voltage, is depend on the configurations or the shape, the size of your conductors, the diameter, the radius, everything, the length of this conductor, and also the thickness, okay, of the insulations. Yeah, the inner radius R1 and the outer radius R2. So the electric field or the field strength is depending on these quantities. Okay, so these quantities or these parameters like voltage, like the radius, the size, everything. And then the electric field, this is related to the property of the materials. Okay, so for this case, we are using solid, right? So we should design the field strength should be less than the electric strength or the dielectric strength, the material strength. So what happens if the field strength more than the electric strength? So this can cause premature failure, the partial discharge, the inception of the partial discharge. So the partial discharge, their theory, everything we will learn in chapter 5 and also the next chapter lah, on the theory of breakdown. Okay. So if the field strength above the electric strength, so the breakdown may happen lah. So this is something that we need to prevent lah. So this chapter is related to design. Okay. We need to understand in terms of the conductor, their shape, right? So what the theory we are using in order to do the calculation, in order to derive the equations. And then some applications, something like in cables, cable accessories, like bushings, what kind of techniques that we can use to control the cells in order to prevent from the inception of the partial discharge. Okay, so we need to ensure this criteria is complied. Right? Okay. Alright, okay. So this is some example in order to trigger everyone lah. Okay. So like cable accessories. So cable accessory we have termination and join. So mostly the cable accessories. So they have we call as the cable entry fitting. Okay. Right. So something like this cable termination basically is used to as part of the entry lah, for something like the switch gear, right, or the transformer. So they are basically installed at the cable compartment. Okay, you can see this is the cable compartment for the switch gear. So this is the elbow shape of the terminations, the elbow type of terminations, right? So this is plug-in termination is called filterer. Yeah, something like this. So this basically used for 3 kV and above lah. So like this, right? So this kind of termination is used for 11 kV systems, right? So they have like this semiconductor screen in order to linearize the electric fields. So basically at this point, so electric field will be very, very high, okay, because this is the entry part, okay, the entry point, right? So the electric field become non-linear, okay. So this cable will carry 11 kV. So 11 kV will enter the 11 kV switchgear, but at this part, the electric field become very, very high. Okay, so that's why we have a few techniques that we call as geometry field grading or capacitive field grading. So we can use something like semiconductor layer to linear the electric fields. We are going to see this, I mean, maybe at the end of this chapter. Okay, so what happens if the electric field or semiconductor screen is not installed at the proper way? So you might see this kind of punctured. Okay, so this is called a breakdown, right? So the insulation is no longer insulating this cable. Okay, and now you can see that this SLP is no longer become SLP. It's become a void, and this will fill out by air. Okay, so we know air, it has lower electric fields compared to the solid insulations. And of course, at a certain voltage level, the discharge may happen and it may conduct the current. Okay, so the discharge happen due to the ionization of the air. Okay, so it can create conductive channels, okay, where the current can flow. So it's no longer become the insulator, then it become a conductor, then the current may conduct. So when the current conduct, then we have a short circuit. So when the short circuit happen, high temperature, high current, then boom, fire may be ignited lah. Okay. So now you can see this is a black layer. So this is called semiconductor layer. Okay. So semiconductor layer, they have different permittivity. So because of different permittivity, so they may linear the electric fields. Okay. So higher conductivity, lower the electric fields. Then they may basically linear the electric field. So the electric field may be distributed away from the stress area. But now you can see because of the installer, okay, the cable jointer. So for your information, we have for medium voltage, we have PK1, PK2, and PK3. Okay, so PK1 can install a cable below 1 kV. Right? So PK2 can install below 11 kV and PK3 can install below 33 kV. So basically PK1 can install low voltage cable lah. I mean 4 and 5 volts. Yep, something like that. Okay. And PK2 and PK3 they are actually competent. Okay, so PK1, this is called cable jointer. So this is something like license given by Energy Commission of Malaysia lah. Okay, so this is for your extra information lah. Okay, so if you work as engineer or you're working as a project engineer or project manager, then you have a cables that you need to install that you might need to find people that have this kind of certifications. Okay, you cannot simply ask someone, like wiremen, they have PW4, isn't it? Yeah, so PW4, right? PW1, so they have different levels and different certification that they are actually endorsed. They can endorse, right? Yeah, for like PK3, they can install something like this plugin. So this is filterer. So this kind of plugin is a little bit difficult, to install because they have more complicated combinations of material inside this. Okay, some component difference and different manufacturer, different specs. Yeah, so of course they should comply with specification given by the manufacturer as well. So basically, this is SLP. This is the insulations, and this is semiconductor screen. Okay, like what we call as the insulator screen, and this is to be cut in a smooth line. So if we have something like non-smooth line or sharp tips, then this can create non-uniform electric fields. Okay, and you might able to see here as well in the cable joint. So this is the ferrule. Okay, so this is might be straight through joint. So this is also SLPE cable. This is also SLPE cables. So they just join. So this is a ferrule. Okay, so this is like a conductor to join between two cables, right? And then you might see here, so this is called deflector, right? Or they call as stress cone. So this is semiconductor materials. Okay, so they are used basically for cable entry fitting. So this is cable entry fitting. So this is used to linear the electric fields. So this is called geometric field grading. Okay, so it grade the electric fields so that electric field will not concentrate at one point, the electric field will be linear out away from the stress point or away from the cable entry fitting. Okay, all right. So what happens if they are not installed at the correct way? So you might see this kind of tracking, a surface tracking, right? Yeah, this something like electrical trees that may propagate a crawling on the surface and finally short circuit between these two conductors. Okay, and then of course a flashover may happen lah. So the cable may break down. So this is what are the things that we don't want to happen lah. Okay. Right. Okay. So this is some other photos. If the design is not well installed, okay, the cable terminations or cable joint, they are not installed at the proper way. Okay. All right. So there are some other techniques lah. So basically we are using something like capacitive or geometry free grading. So this is called a stress cone. So they have deflector. So deflector basically is used to guide the electric field at this cable fitting point. Okay. So when we install cables or terminations to another conductor of the switchgear, then the higher electric field will be happen at this area. Okay, so that's why we require to have like another semiconductor materials so that it may reduce the electric fields. And you can see the shape is it has something like a simple curve. So this simple curve is to guide the electric fields so that the electric field distribution will be linear out in this way, in this line. Okay, or you might able to see here. So you might able to see that the electric field will be higher at this point. Okay, but what happen if we have this kind of deflector, the stress cone? Now you can see the electric field linear out, and then their potential little bit equipotential is compared to this figure that without the stress control. Okay, all right. Yeah, so this is another thing. They are actually the same thing. So if we don't have like this deflector or the grading cone, so electric field will be concentrated at this point. Okay, so that's why it might trigger the electrical trees. So this is the other things that we don't want lah. All right. Okay, so this is another feed control tubes. So we can use different permittivity so that it may guide the electric fields so that it may not be concentrated at just one point lah. Okay, so this is can be used by using reflective grading technique by using high permittivity materials. So we put another layer here or coating, and then with the higher permittivity, right, then it may guide the electric field lah. It just concentrate 25% at this area, and then 25%, 75%, and 90%, right? So it guide the electric field so that electric field are not concentrated at just one point. So this is very important. Okay. So we have two type of cables. So we call as medium voltage cable versus the high voltage cable or extra high voltage cable. So this is depend on their voltage, something like 11 kV, 22 kV, or 33 kV. So this is a typical voltage level for medium voltage cable. And high voltage cable like 66 kV, 132, 275, or 500 kV. Okay, so this is for extra high voltage cables. So you might see that this is medium voltage cables. this is extra high voltage cable. Based on their design, they are actually the same. Okay, so the design, they are the same. They have conductor, conductor screen, insulator, insulator screen. They have the cable sheets, right? So for the conductor, they have the jacket, right? So they might have also armor for extra mechanical protections. Sometimes armor is also grounded, sometimes not grounded. It depends on the power system design. Either it may carry the fault current or not. Okay. But of course, if you see for medium voltage and extra high voltage cable, they are of course the same. So the difference is their thickness of the insulation, the SLP, right? So the extra high voltage is a little bit thicker. So why? Because it carry higher voltage, right? More voltage than medium voltage. And then, but the main difference that we can see is that what is their field stress. Okay, so this is something that we can see. The only person that designed the cables, yeah, he should know about it. Either he's using analytical method or numerical methods for designing or to simulate the electric fields. And something that we cannot see is voids, right, inside these SLP insulations. Okay, inside the insulations, right? Of course, the medium voltage cable, it may accept bigger voids, I mean, in terms of diameter, but the extra high voltage EHV cable or HV cable, it cannot accept bigger voids, I mean, bigger size of void. Okay, why? Because of the higher voltage, something like 275 kV or 500 kV, the electric field is more than the medium voltage cable. So that's why it cannot accept more voids or the more gas filled void or air filled voids inside the SLP. Okay, so that's why these cables, either medium voltage cable or extra high voltage cables, they must be tested. There must be commissions before they are allowed to be applied or to be installed in the field. Okay, all right. Okay, so you might see that the medium voltage cables. So basically the electric field. So this is I took from can't remember. This is coming. Maybe I took from Secret or IEEE or IEC brochure or standards, right? So you might see that the medium voltage cables, so their electric field is within 2.5 to 4.5 kV. But for high voltage or extra high voltage cables, the electric field is higher, okay, compared to medium voltage. So that's why they cannot tolerate bigger void inside the SLP lah, inside the insulations. Okay, so when we calculate the electric fields, so the higher electric field will be happen or occur on the surface of the conductor. Okay, so this is copper conductor, this is SLPE, this is cable sheets that basically will be grounded, right? Okay, so based on the calculations using analytical method or numerical method, then we might see that the higher electric field will be on the surface of the conductor. Okay, and these electric fields should be lesser than the electric strength of the insulation. Okay, so basically SLPE, it has like 100 to 300 kV per millimeter. Okay, and now you might see that the electric fields at the surface of the conductor, if the voltage that we apply is somewhere around 11 kV to 23 kV, so the electric field will vary within this range, 2.5 or 2.5. So of course you might see that this field strength value, of course, is less than the electric strength of the SLPE. Okay, this is acceptable. And of course, this cable can be energized, can be installed in the field and can be energized. But, okay, what happens if we have a voice? Yeah, so this is happen due to poor manufacturing process, due to degassing or vacuum process. They are not done incorrectly, and some air pocket may be trapped inside the SLP. So because this is air, right? So we know that air is their dielectric strength is around 2.4 or 3 kV per millimeter, right? Yeah, but then you might see that the field strength at the surface of this conductor will vary within this. And this, of course, this value might exceed the breakdown strength of the air. And then what happen? A discharge may start to happen. And this is called electrical tree. So electrical tree is conducting channel. It can conduct the current. And then finally, it may bridge between the high voltage conductor and the ground, and the current might flow. And this is called a short circuit current, and the flashover, the breakdown may happen. Okay, so this is something that we need to prevent from happen lah. Okay, so that's why all cable should be tested first. They have the routine test, and then we need to monitor and identify their quality lah. Okay, so this is can be done by partial discharge technique, partial discharge measurement, and this is we will learn in the chapter 5. Alright, okay, so I think I took quite longer time just for introduction before we move to the physics behind it. Okay, so I try to go quite fast. Alright, okay, so everything is started from the electric fields. So when we have a voltage being applied on the conductor, so then we might have the electric fields. And this electric field is actually a mechanical force that basically exerted on a charge. Okay, yeah. So when let's say we have conductor, right? So we have, or maybe I take a electrode, sphere electrodes. Then we apply a voltage, right? So we apply a voltage, then a current may flow. So when current flow, then this conductor will be ionized. Okay, so this conductor will be ionized. Okay, because the current is rate of change of the charge. Okay, so when we have a charge on the surface of the conductor or surface of the electrodes, okay, then we might have something like the electric fields. Okay, so electric field maybe point out because charge is actually a source, a positive Q. This is actually source of electric field. Okay, negative Q is actually sink of the electric fields. Okay, so we might have the electric fields. So a field will be created surrounding the conductor, and this kind of field is called electric fields. So this field we cannot see, okay, but we can send it, okay, because it create a mechanical force, okay, and this force will just function on the charge, okay. So this is a mechanical force exerted on a charge, okay. So then we have this a force is actually the product of Q and the electric fields. Okay, so this force is a vector. It has magnitude and directions. Of course, for electric field as well, it has magnitude, a certain value, and of course, it has directions. Either internal, either external, either pointing out, either pointing in. So it depends. Okay, yeah. So now you can see that this field will be surrounding the electrical charge, Q, and then it exerts a force on all other charges in the fields, either attracting or repelling them. Okay, so same polarity. Of course, they will repel. Different polarity they will attract. So this is depend on the forces. Okay, all right. Yeah. So, but then we can take the analogy of this gravitational force. Okay, where we have the any mass. Okay, any I mean any components or any elements with a mass, then it will have a force, and force is depend on the gravity lah. Okay, so the same thing also happen to the electrical charge. All right, so electrical charge, we might have a force. So positive charge will pointing down, negative charge will pointing up. Okay, so like charges polarity, so they may repel. Unlike charges polarity, they attract lah. Okay, so this is explained by Coulomb's. Okay, so this is called a Coulomb's law. Coulomb is actually a unit for charge, and this forces that exerts between two charges, right? So it's actually calculated using this formula. All right. So they have different charge magnitude, and R is actually the distance between two charges, right? Yeah. So it's actually D lah, the distance between two charge, right? And K is actually 4 pi epsilon naught 1 over, and Q1 and Q2 is actually the quantity of the charge lah. Alright. Okay. So basically, the force can be calculated by using this formula. Alright. Another important laws. So we call as Gauss laws. So Gauss laws. Let's say we have just now, like we have the electrodes, where we have a charge on the surface of the electrodes. Okay, so when we have a charge, we have that we call as electric flux. Okay, denoted by D, capital D. So this is actually we call as electric flux. Like a line which is produced by a charge. Okay, on the surface of the electrode, because we energize these electrodes, this metal, and a charge will be accumulated on the surface of the conductor, and then because we have charge, the charge may produce electric field line. Okay, and this electric field line is called flux, electric flux D, or sometimes they call dielectric displacement density. Okay, but basically I'll just make it as flux, electric flux, right? So what happen if we integrate this flux, okay, around the area of it? So d dot dA, we integrate it, okay, of the closed area, and this will equal to a charge or total charge, okay, on the surface of the electrodes. And this is invented by Gauss, okay, so this is called Gauss laws. So in order to find the total charge, so we need to integrate the dielectric displacement density, which is electric flux, over the area, and area must be the enclosed area. Okay, all right. So Gauss law is very important lah. Okay, so another way to derive a Gauss laws, so we can derive by Maxwell equations. Right, so Maxwell equation, we have three different parts. Okay, so the first part is the field equations. So this is Faraday's equations, Faraday's law, and the second is Ampere's laws. The second part is continuity equations, and the last part is the material equations. Okay, all right. So by using the Faraday's law and Ampere's law, we can derive the Gauss laws. Okay, so basically, let's say we have like a conductor, so we apply a current. Okay, so this kind of current we will use J. This is called a current density, right? And then because we have a current flow inside the conductor, so it will produce a charge on the surface of the electrodes. So this charge will produce a flux D, right? And this is the air part, I mean the outside the electrodes. So the electrode is a conductor, right? So according to the continuity equations, so J is the conduction current, and D will produce that they call as displacement current. So according to the what they call it, the continuity equations, J dot dA is equal, when we integrate it, so this is equal to a conduction current, right? And then when we integrate d dot dt, d dot dA, this is also create a current. So, but this current is called displacement current, right? So, according to the continuity equations, so J dot dA plus this integration delta d dot dA, right, will be equal to the total current. Okay, so it will cover inside the conductor and also outside the conductor, right? Yeah. All right, so in the beginning, so this current will be equal to 0. Okay, so this current will be equal to 0 lah, right? And then finally what we are going to see that, yeah, so we can make it simple, J plus the D the sorry, right, equal to 0. Okay. All right. So this actually equal to the current lah. Okay. And then the d dot dA is equal to, right, negative J dot dA, right? Okay. Yeah. So this is actually also equal to the current lah. Okay. So when you bring this to this side, okay, then you might able to see that delta D dot dA will be equal to J dot dA, and this is actually the current, and multiply by delta T. Okay, so all of this actually a Q, right? So this, all of this actually a Q lah. So the integration you might need to maintain it. So then finally you might get D dot dA is equal to Q, and this is called as Gauss loss. So this is another way to derive the Gauss loss, but basically we are using Maxwell equation, the field equation, and also the continuity equations. So this is, I think you all already learned in very detail in the EMT subject lah. Okay, all right. So I just want to refresh again lah, in the way how we get these equations. Why this equation, the Gauss law equation, is very important? Because the Gauss law is used to derive the electric field strength on different shapes of the electrodes. So this is very important, and this is called analytical technique. All right, okay. So I already discussed about it. Okay, so we have two types of electric fields. So the first electric field is called uniform electric fields or homogeneous electric fields. So basically, switchgear, the cable, the transformer, all these power equipments, so they all should be designed in homogeneous fields. Okay, yeah. So there should not be any non-uniform electric field. So electric field should be uniform. Okay. So if a non-uniform electric field happens inside the transformer, inside the switchgear, right? So what happened? It may degrade the quality of the insulations over the time. Okay. Yeah. So it may take maybe years to cause the failure. Okay. So that's why as the engineer, the design engineer, so this electric field should be controlled so that it should be uniform at every point or at every parts of the components, right? And then how we know the electric field is homogeneous or uniform? Let's say that we take here, right? Okay, this parallel plate electrodes. Okay, so we have here top electrodes, we have bottom electrodes, top electrode and bottom electrodes. Okay, so then you might see that, let's say we just take 3 points, 1, 2, 3 at the top of the electrodes, and 4, 5, 6 at the bottom of the electrodes. And then when we draw a line of electric fields, right? So you might see that they have the same point for the top electrode and the same point at the bottom electrodes. So we can say that because of they have the same number of line, you can draw more line, doesn't matter, but they still have the same point, okay, the same point for the bottom and the top electrodes. So this is we call as uniform fields, okay. And basically we will draw the equipotential line. So this is the voltage line. It basically will be at the right angle of the field line, electric field line. So this is field line, will be orthogonal to the electrode surface, and the voltage or potential line will be parallel with these electrodes, okay, and then they create a right angle. So if they create the right angle 90 degrees, then they also considered as uniform electric fields. Okay, all right. How about for non-uniform electric fields? For the case of point to plane, so we have a needle, okay, with the sharp tips and a parallel a plate, okay, a plate at the bottom. So then what the field line will be created? It will create a line that will bend out here. And now you might see that just one point at the top and at the bottom we have 6 points. So they are not balanced. So this is also called non-uniform electric fields. Okay, so this is the way how we understand the difference between uniform electric field and non-uniform electric fields. Okay, yeah. So another case like this ball-to-ball electrodes, okay. Yeah, basically the electric field will follow the shape of the what they call it, the electrode lah, okay, and then the electric fields, yeah. So you might see that the electric fields also not very good lah, okay. They are not orthogonals, okay. Some point might be orthogonal lah, okay. Some point is not, right? Yeah. Okay. So this is potential line, and this is the electric field line. And then some point they are actually 90 degrees. Some point they are not 90 degrees. So this is called quasi uniform. Okay. So in order to make it uniform, the diameters, okay, the diameters of the electrodes, okay, should be bigger than the distance, okay, right? So then the electric field will be more towards uniform, okay. So but this is still called quasi uniform, okay, but this is still uniform, okay. So this is still called still called as uniform, but this condition should be complied. So the electrode diameter should be bigger or should be more than the distance between these two electrodes. So if the vice versa, then it become non-uniform. Okay, so this is for the case of ball to ball, okay, ball to ball, two sphericals, right? So you must able to see that this in some applications, so they are using this ball to ball in order to study um, the the quality of the oil, right? They say like the power transformer. Okay, the power transformer, you have oil, right? So the power transformer, they have this is transformer. They have bushings at the bottom and also at the top of the tank of the transformer. They have a drain valve. Okay, where they sample the oil. Okay, yeah. So they like maintenance engineers or the project engineers. When we install the oil, okay, to insulate the and also to cool down the temperature of the winding. So this basically we had the winding red, yellow, blue, right? Okay. So we sample, we open this drain valve, and then we take some small sample of oil, basically less than 1 liter, and then we have equipment we call oil test set. Okay, so this is comply to the IEC 60156. So this IEC, they have the standard procedures, the method, the procedures how we conduct this breakdown voltage. Okay, so they in this the oil test sets, they have this a cup or test rate. Okay, so they have two ball electrodes, right? And then basically the distance is 2.5 millimeter, if I'm not mistaken, 2.5 millimeter or 2.5 centimeters, right? So need to check this standard lah. Okay, yeah. But this ball electrode is around 6 millimeter. So you can consider that 6 millimeter is more than 2.5 millimeter. Then you have this COESA information, COESA uniform electric fields. So we apply a voltage, okay, on these electrodes, the ball electrodes, and then pump, the breakdown may happen, okay. And then we take a value lah, we take our breakdown voltage, right? Yeah. And then the breakdown voltage should be more or equal than 30 kV lah. And this is for medium voltage level. If for high voltage level and extra high voltage level, this breakdown voltage should exceed 35 kV. Yeah. So this is, if I'm not mistaken, this is according to 60422 lah, the IEC. Right? So this standard mention about the acceptance limit lah. Okay. So the breakdown voltage of this oil, this transformer oil. So when we sample, so basically we take once a year, right? So once a year during the energized condition. So while this transformer energized, we can just open this drain valve, and then we can sample out some small amount of the oil lah. Okay, then we send to the lab, where the lab have this equipment oil test set, and then we run. Then finally we can know this their breakdown voltage. So what happened is the breakdown voltage less than 30 kV. Then we need to shut down the transformer, and then we need to filter down the oil. So because the oil has impurities, wet fibers, or maybe the moisture or water is already ingress inside the oil. Then that's why the voltage fall down lah. Okay, yeah. So we need to do what we call as oil reclamations. Yeah, but in the standard IEC 60156, we are allowed to use a ball bearing and also we are allowed to use a parallel plate. Yeah. Okay. This is to simulate uniform electric fields. Alright, okay. So I already mentioned about the equipotential line. Alright, okay. So where we apply our knowledge of the electric fields. So we actually apply this knowledge for designing certain components of the that we basically use in our power equipment, something like the bus bar, like bushings. Okay, so bus bar can be a bare bus bar, and also it can be insulated bus bar. Okay, so different voltage level, we might have different system. Okay, different systems. And insulated bus bar is used for higher electric fields, okay, compared to a bare bus bar. Okay, all right. Why? Because we have the insulator, right? And if you go to something like Petronas, so Petronas now they are more using the insulated bus bar compared to bare bus bar, because the insulated bus bar provide more protections. Okay, in case something fall down and touch the bus bar, so there will not be any tripping on the relay lah, on the protection side. Okay. Yeah, because the bus bar is already insulated lah. So when it's insulated, then it's allow higher electric field, higher voltage can be used or can be applied on the bus bar. Okay. And the bushing as well. Bushing is using for like higher voltage or extra high voltage. They are using condenser type bushing. So inside here we have a foil layer, and this would create a capacitive grading layers. Okay, so this is will distribute the electric fields along the bushing lah. Okay, so we are going to study this maybe on the end of the slides. Like cables, like other transformers. So this is very important in order to reduce the electric field, something like in cables. So the cables, we have voids that may reduce the quality of the insulations, and then the void may cause a failure lah. Okay, so that's why we need to study in quite detail, especially on the electric fields at different, let's say we have different materials, and then we have watts. Okay, and this is the air pocket. Then it may reduce the electric fields, right? Because due to different permittivity, the lower permittivity, the higher the electric field. So we are going to see this on the next slide as well. All right, okay. So in order to study the field distributions, we will focus on different shape or different size of the electrode or the conductor. Okay, so basically the idea is come from a point charge and line charge, right? Yeah, but everything is derived according to the Gauss laws, and the Gauss laws is depending to the surface charge, because we are taking d dot dA. Okay, yeah, so the enclosed charge on the surface of the electrode is equal to integration d dot dA, and d is actually the flux that produced by the charge. Okay, and then this will be a total charge enclosed on the surface of the electrodes. So we will focus three conditions. Okay, three main conditions. So the first will be symmetrical sphere in the free space, like this. And symmetrical or concentric sphere. Okay, so where it has another sphere for the outer layers. Okay, for the outer layers, you have the inner layer with the inner radius, and it has the outer layer, okay, with the outer radius lah. Okay, this is for the case of example of the concentric capacitor, right? So where it has the inner electrode, the sphere electrode, and it has the outer electrodes, also sphere, and then in between of these two sphere electrodes, so it has the insulation in between. Okay, so this is called symmetrical concentric sphere lah. Okay, and another condition we may also consider is that a cylindrical. Okay, all right. So this also can be either concentric or not lah. So we consider these three shapes in order to derive the equation lah, according to the Gauss laws. All right. Okay. So in order to determine the potential distributions, okay, we are consider three techniques. Okay. So the first technique is the analytical calculations. So this basically according to Gauss laws, where we just consider Laplace condition. We are not consider Poisson's, because Poisson is consider for space charge with the availability of the space charge. Okay, but for our case, we just consider the space charge free effect lah. Okay, and then the second technique, this is conventional techniques. We are using the experimental technique. So this is by using the electrolytic liquid, or we can just use this is called a field plotter, or we can use something like whether this is paper or this, or we can call it semiconductive paper lah. Okay, so these two technique is using experimental technique. So before the analytical technique or numerical technique has been invented. Okay, so the last technique, this is more accurate, is using numerical computational technique. So we have a few techniques like the finite differential method, finite element method, boundary element methods, and some other method like charge simulation methods. So that will not be covered in our syllabus. For our syllabus, for considering the simplifications, we will just consider finite differential method to calculate the electric fields. Okay, so this is called numerical technique. So numerical technique required calculation has been done in order to calculate the value of the potential and also the electric fields. Okay, so for the first step, we'll go quite detail on the analytical technique. Okay, and then we will see quite surface on the experimental technique, and we will go quite detail on the calculation for the potential and also electric field for the finite differential method. We are going to apply the FDM method in order to calculate the equipotential line and then analyze the electric field distributions. All right, okay. All right, Okay, let's see what is the analytical technique, right? So for the analytical technique, we need to employ 5 steps. Okay, so the first step we need to apply these Gauss laws according to these equations. And then after we get the Q, right, the total charge on the surface of the electrodes, right? So we will calculate Q in the function of maybe radius of the electrodes. And then finally, we will calculate the potentials. And potential will be calculated using this formula. We need to integrate the electric field over the distance. Okay, depends maybe from the radius, the inner radius to the outer radius, or maybe the inner radius go to the infinities. Okay, so this is for the case of the sphere electrodes in free space. And then after we find Q, the charge, and also the potential, the voltage, then we can calculate the capacitance. Okay, so because the capacitance is where the energy has been stored, okay, yeah, inside the insulations, inside the electric fields. And then after that, we need to calculate the electric field in the function of the distance, or maybe radius, right? Yeah, so this is in the function of radius. Then finally, we need to calculate the maximum electric fields, so that we can understand based on our design, maybe the shape, okay, the size of the radius, okay, R1, or maybe bigger R1, bigger radius of the electrodes. So the electric field will be different. Okay, so then we need to know that the electric field, the maximum electric fields, either is depend on the radius or not. Okay, yeah, so this is what we need to find. We need to find out. And then finally, we need to use the optimization method so that we can calculate the minimum electric fields. Okay, yeah. So we may consider a spherical, cylindrical, and also a parallel plate condition. Okay. So let's see for the first one. So we have this kind of electrodes. So basically, this electrode, let's say you have like a capacitor, a spherical capacitor, okay? So, or maybe electrodes that is hanging on the space, hanging on the space where we have something like a wall, okay? So the distance of the electrode from the wall is very far away, okay? And then we might consider the distance might be the infinity because it's very far away, okay? Yeah, so it doesn't have outer radius, okay, but it has the inner radius, so this is called R. Then we need to find out how much these electric fields, okay? So at what part or at what point the maximum electric field may exist. Okay, we need to find out. So this can be done by using analytical technique. All right. So then after we calculate the analytical technique, according to the analytical technique, then we can plot the electric field distributions. Okay. So according to this spherical electrode hanging in the free space, then we might see that according to certain voltage levels, the higher electric field will be at the position of the surface, okay, at the surface of the electrodes. And then you can see that the electric field, I can't remember what voltage I put here, but you might see that this electric field can go up to 3 kV per millimeter. And if the electric field reaches 3 kV per millimeter and this ball electrode is surrounded by air and the electric field exceeds 3 kV per millimeter, so it can cause some discharge, okay? Some corona discharge may happen on the surface of the electrodes. Alright, okay, so what happened is we have another type, this is called concentric sphere. It has the outer radius, so this is called R2, and from here to here is called R1. Okay, so then you might see that when we have the outer radius, the electric field going higher than this, higher than this the ball electrode hanging in the free space. Okay, so after we have the R2 on the outer radius, the electric field will go higher. So we have two different conditions. Okay, so this kind of the concentric sphere, it can be used at different applications. Okay, so that's why we need to study different application as well. All right, so let's see how we use this analytical technique. So the first thing we use the Gauss law equations, right? The Gauss equations, d dot dA equal to Q. So because of this, if we refer to this figure, you might see that this D, right, is actually constant over the surface of these electrodes. So because this is constant, we will take out from the integrations, and then we just integrate only the surface area of the electrodes. So this is for the case of spherical electrode in the free space, and the outer radius is very far away and is considered infinity. And then because this is spherical, the area will be equal to 4 pi multiplied by radius squared. Okay, and then this will be equal to the charge on the surface of the electrode. And then finally we can get the flux density is equal to Q over A lah, right? And the flux density is equal to permittivity multiplied by the electric fields, and the permittivity is equal to epsilon naught, permittivity of free space, multiplied by relative permittivity, which is related to the materials, and then multiply with E lah. Okay, alright. So I think this will be a simple equation to memorize. But the question is, what is this epsilon? Okay, yeah. So epsilon is actually property of the materials. Okay, maybe solid material, liquid material, gas materials, right? So this is insulating materials. So they have different properties, different value of the epsilon R. Okay, so the higher epsilon R, more electric field will be permitted to flow inside the materials, either gas or air, either solid or liquid. So they have different epsilon R value. So the higher permittivity, more electric field will be allowed to flow or to penetrate the materials. So then finally we get the electric field equations. So Q divided by 4 pi epsilon R squared, right? So this is equation that we want to know. Then after we got this equation, we can get Q and V, right? So then we integrate, yeah, E over dx. So E into dr Okay, because we integrate from the surface. Yeah, we integrate from here to the infinity. So because we want to know what is the electric fields. Right. Then finally we got these equations, the voltage from surface of the electrode, right, over the infinity, right, to the infinity. Then we can get this equation Q over 4 pi epsilon R, and Q will be equal to Q will be equal to 4 pi epsilon R multiplied with V, and capacitor is actually the division between Q and V. Q over V is the equation for the capacitor, and then the capacitance is equal to 4 pi epsilon multiplied with R. R is actually the radius of the spherical electrodes. Alright, and then we use the equations. We simplify from these equations. Then finally we got E in the function of inner radius and the distance. Okay, yeah, the distance from the surface to the infinity, right? Yeah. So based on this equation, we can plot the the field, electric field graph. So this will be ER and this is R. And then finally, we can see that the maximum electric field actually at the surface of the electrodes. And then the electric field will reduce inversely in the function of 1 over R squared lah. Okay. And then finally, we can know that the maximum electric fields is equal to V divided by R. So when they are equal to inner radius, okay, yeah. So when these are equal to R, so then the electric field will be the highest one. Okay, yeah. So one thing that we can know that, so if R is smaller, then the higher the electric field will be happen. Okay, yeah. So this is something that we need to prevent from happening lah. Okay. So that's why if we are using a small ball compared to bigger ball, okay, smaller ball, smaller radius of the ball's sphere will produce higher, sorry, not voltage, higher electric fields. Okay, yeah. So smaller radius, the higher the electric fields. So that's why this should be prevented to be happen lah. Okay. All right, another example for everyone to see. So step 1 will be the same. So this is for spherical capacitor, right? Spherical capacitor. So, sorry. So where R2 is finite. So we have a certain value of R2 lah, right? So R2 we have a certain value of the radius. And step 1 to find D according to the Gauss laws will be the same. And also find E also will be the same because it has also 4 pi R squared, the surface area. And then, so when we calculate the voltage, so we will derive from R1, the inner radius, to the R2. And then finally, we get these equations. And then equation for capacitor will be Q divided by V. And then finally, we find the capacitance value for the spherical capacitor. And then for electric field distributions, so we might see that we have another R1 and R2 here, and also still the same. So the distribution of the graph will be inversely proportional to 1 over R squared. Okay, so this is R, this is E over R. Okay, and then we need to use this equation to plot the graph. And then based on these equations, then we need to find at what point we have the maximum electric fields. Okay, so the maximum electric field happened, it found that when R, this R, the distance, okay, away from the surface of the electrodes. So when R is equal to R1, the inner surface, the inner radius of the inner radius of the inner electrodes. Okay. Yeah. So this is R1. So this is the inner electrode, and this is the outer electrodes. So we have here R1, and from here to here is R2. Okay. So this is R. So when R equal to R1, according to this equation, so when this R equal to R1, then electric field will be the highest one, the maximum one. Okay, yeah. So that's why you might see that the highest electric field, so this is the E max, will be happen at R1. And R2 maybe somewhere around here. Yeah, where electric field will be lesser than electric field at R1. Yeah. And then we substitute small r with R1, then we have these equations for the maximum electric field in the function of inner and outer radius and also the voltage. Okay, so this equation is important in case we know R1, we know R2 according to our design, and then this is the applied voltage that we apply. Yeah, so maximum phase strength happen when the distance equal to the inner sphere, okay, the inner radius of sphere. Alright, okay. So another thing that we need to know is that we need to find what is the minimum electric fields. Okay, so that we can design a suitable R1 and R2 lah, the inner and also the outer radius. Okay, so the minimum electric field may happen when R1 equal to half of R2. Okay, then we will get the lowest ever electric fields. So this is important lah, because we want to have the minimum over electric fields, so that the electric field may not exceed the dielectric strength or electric strength of the insulations. Yeah, the idea is like this. Let's say we have the inner and the outer radius. So between inner and outer radius, we fill out with air. Okay, and we know the electric field of the air cannot exceed 3 kV per millimeter. Okay, so that's why we need to design a suitable R1 and suitable R2 so that it may not exceed 3 kV per millimeter. So what happens if exceed the dielectric strength or electric strength of the air? Then it can cause flashover. Then a short circuit may happen between these two electrodes, inner and outer electrodes. Yeah, so we understand that the highest electric field will be at the surface of these inner electrodes. But in order to reduce the electric field to the lowest ever, then we need to design the R1, the inner radius of the electrode, should be equal to the R half of the R2, so that we can have the minimum electric fields. Yeah. All right. And also we, according to our design, we have already R1 and R2. Then in order to prevent the electric field so that it may not exceed 3 kV per millimeter, if we fill out the insulation with air, then another parameters that we can control is we can reduce the voltage. Yeah. So we reduce the voltage, then the electric field will reduce as well. Yeah. So that's why the air, let's say like air insulated switchgear, so it's just limited for application up to 11 kV. Okay. Yeah. If you want to use more than 11 kV, we need to use gas insulated switchgear. So this is using sulfur hexafluoride. Yeah. Sulfur hexafluoride, the electric field cannot exceed 9 kV per millimeter. Yeah. So it is stronger 3 times more than air. Okay. Yeah. So that's why SF6 has been used for 33 kV, medium voltage cable, or 132 gas switchgear cable, gas switchgear. Yeah. So why? Because the electric strength of the the SF6 is better than the air. Okay. All right. So then you can use higher voltage here. Depends on the insulation that we use inside between the electrodes. Yeah, yeah. So then you can see the comparison between these two type of electrodes. So the first is spherical electrode in the free space, the first condition, the first design. And the second design is the spherical electrode with the known counter electrode with the R2. Yeah, like the concentrate capacitor just now. Then when we have the outer electrodes, the electric field will be higher, okay, compared to the electrode that without the outer electrodes. Yeah, so this will be the same as what I used here, right? Yeah, so the blue line is for with the outer radius R2. R2 is finite. But for red line here is when R2 is equal to infinity. So you can see that the electric field is lower. All right, okay. Okay, actually I have oh yeah, it's here. Stop sharing. All right. Okay, I hope you all can see my Microsoft Excel here. All right, okay. So this is I use Microsoft Excel in order to simulate the electric fields according to the analytical technique. So this is used for two conditions here. So one is the spherical shaped electrode with infinite radius, the outer radius, and one with the finite outer radius, the counter electrode, okay, with R2. All right. So then according to the formula, right, so we can get the minimum electric fields we can get the minimum electric fields when R1 is equal to R2 divided by 2, half of the R2. Okay, so now you can see here I take R2 is 60 and R1 is half. Then I apply 11 kV. I using the same equations. Yeah, so this is to get the optimizations. So R1 should be half of R2. Then we can get the lowest ever the electric field with respect to the applied voltage, 11 kV. Let's say I increase for 11 kV, you can see here the electric fields is equal to 0.73 kV. Yeah, so somewhere around here. Okay, but if I increase the voltage, let's say I increase to 132 kV, 132 kV, then you can see the electric field is going very high and it goes to 8.8. Okay, yeah, so this is the minimum ever that it can get lah. Okay, the lowest ever. But what happen if I do not use this optimization method? So what happen, let's say I reduce the, or I increase the inner radius. Let's say I put here 40. Yeah, now you can see it's go up. Yeah. Yeah, according to this voltage 132 kV, if I choose 60 millimeter for my outer radius, my inner radius should be half of it, of the outer, so that my electric field will reduce. So I can get the lowest ever is 8.8 kV. Yeah. So in between these two electrodes is inner and outer electrodes. So I cannot use air. Yeah, because air will flash over, it will break down when the electric field over 3 kV per millimeter. But now you can see the highest electric field is actually at the surface of this R1, the inner electrode. But the electric field is go very high, up to 9 kV per millimeter, 8.8 kV per millimeter. Okay, I have two options. Okay, either I increase this, let's say I use 80 and here will be 40. Yeah, so now you can see the electric field will reduce. Or I need to use different insulation materials. I cannot use gas. I need to use a better insulation. Yeah, either I use solid or I use liquid. Okay, because their electric strength is better. Okay, like SLP is 100 kV per millimeter. Yeah, so it is very strong. Okay, like liquid is 30 kV per millimeter. Yeah, so according to this electric fields, so you can see the maximum here is 6.6 kV per millimeter. Then I can use SF6 because SF6 will break down at 9 kV per millimeter. Yeah. Okay. Or I can use oil around 30 kV per millimeter. Yeah. So that is the design. Or I make it bigger, maybe 100 millimeter, and this is 50 millimeter. Yeah, now it's reduced to 5 kV per millimeter. Previously 6.6. Yeah. but the size will be bigger lah, right? And of course, when the size is bigger, the cost will be added lah. Okay, the cost also will be increased. Yeah. So then you may require a bigger space for installation and for storage. Yeah. Right. Increase certain area, then make it the system bigger systems. Yeah, it should be a compact systems. Yeah, when you want to make it compact, smaller, then of course you need to reduce the voltage here. Let's say you want to make it compact, 20 millimeter, and here should be 10, but now you can see the electric fields go very high, 26.4 kV. So what you need to do is you need to reduce. Let's say it's just suitable for 11 kV. Yeah. Now you can see if you reduce the voltage 11 kV, then electric field also will be reduced. Yeah. Right. So it cannot be used above 11 kV. Let's say if you want to use air, because air will be break down around 3 kV per meter, and this is still able. You still can use it because this is still 2.2 kV on the surface of the inner electrodes. Yeah. What happens if you want to use for 33 kV for these compact systems? Yeah, it's still 6.6. Then you cannot use air. You need to fill this system or this electrode system with the SF6 gas. So SF6 gas will break down at 9 kV per millimeter. Yeah. So this is the design that you need to consider lah. Okay. Let's say if you have a bigger space, then of course you can use at a higher voltage, and then you can reduce the quality of the installations. Of course, if you gas is cheaper compared if you want to use oil, because the oil you need to consider also the sealant, everything. Okay. Yeah, the fitting, right? So that not have leaking. And then if you use like solid insulations, like a maintenance, something like a design, you want to shape the solid, also it can be a little bit challenging. Yeah, compared if you want to use gas. Okay, but if you want to use gas, then you may need to consider voltage, apply voltage, inner and outer radius for this kind of shapes. Okay, of the electrodes. All right. Okay. So hopefully it open some insight lah. Okay. So that everyone can see the applications. All right. Okay. The last one is on the cylindrical field. So cylindrical field has been used a lot. Let's say like the cylindrical shape. This is coaxial shape, right? Yeah. And this is with the outer, right? Okay. Yeah. So this is also used for cable, for gas insulated switchgear, for gas insulated line, for conductor of the bus bar, right? The IPB, isolated space bus duct, okay, for the bus duct. This is if you visit like power plant, okay, you might see that they are using the IPB in order to connect between generator, step-up transformer and generator. So in between they want to connect this generator, step-up transformer and generator, they are using the IPB. Okay, so IPB is just like this cylinder. It's like a cylinder, but inside it has a bus bar, a conductor lah. Okay, and it's actually insulated by porcelain insulator. Okay, right. Yeah. So This is another shape of cylindrical, right? So that we need to design, we need to know the inner and outer radius R1 and R2, right? According to the length of the cylinder. Okay, so how we know the electric fields, right? Of course, the electric fields depend on the voltage, depend on R, depend on R2, right? Okay, so then we are using the same thing because this is analytical technique. We are still using Gauss law for the step one, the same thing. Yeah, because the field density is constant over the surface of the electrodes, but the area will be equal to 2 pi Rz. Z is the length of the cylinder. Okay, and then we finally got these equations, and then the same thing will be integrating from position R1, the surface of the inner electrode, until the surface of the outer electrodes, R1 to R2. We integrate it because we want to know the voltage distribution and also electric field distribution. And finally, we got these equations. We got ln R2 over R1. And then we also need to find how much the energy is actually stored, how much the capacitance, okay, in between R1 and R2 lah. Okay, and then we got the electric field equations, right? We just from these equations, right, we know the voltage, and then we know Q, then we just convert it in the function of R, the distance, the outer radius, and also the inner radius of the electrode, and then the applied voltage. Yeah, and then this will be a general equation for a cylinder. Then finally, of course, we need to know how much is the maximum electric field and at where. Okay, yeah, the position at what positions. Then finally, we know that when this r, small r, the distance, equal to the inner radius, then we got the highest electric field. This is actually like a skin effect. Okay, the skin effect. So when small r, the distance equal to R1, the inner radius, the radius of the inner conductor, then we have the maximum electric fields. So it means that the smaller R1, then the higher the electric field. So we must control the size of R1 so that the electric field may reduce. Okay. All right. Then we are using the field optimizations. So the field based according to the field optimizations, the minimum electric field can exist when R1, the inner radius, equal to the outer radius divided by E. E is actually 2.71 something. Okay. Yeah. The exponent, right? Yeah. So then the electric field will be the lowest ever. Okay. But of course, it still depends on the applied voltage lah. All right. Let's see the example. All right. Let's see the example. Okay, let me share the Excel. Yeah. Okay. Hopefully you all can see, eh? All right. Okay. So in order to achieve the lowest electric fields, then R1 should be designed equal to R2 divided by exponent, right? So let's say we choose R2 is 5 millimeter. Okay. and then we apply the voltage 4.2, then R1 must be equal to R2 divided by exponent. Then we can get the minimum electric field is equal to 2.2 lah. Okay, 2.2. Okay, let's say we choose smaller R2. Okay, let's say 2. Alright, yeah. Then electric field will be higher. Okay, yeah. So let's say we want a compact systems, small systems, then yeah, the R2 will be reduced, right? Yeah. So the optimum one it should be 0.73. Okay, 0.73. So then the electric field will be lower lah. Okay, electric field will be lower. O3. Alright, it should be O3. J3. C3. Yeah, C3 multiplied by exponent 1 divided by O3 divided by O3 here. Yeah. Right. So the R1 should be 0.73 lah. Okay, if R2 is equal to 2 millimeter, let's say we want bigger systems, right? Now you can see if you're bigger, then of course the electric field will be reduced. But if you are bigger, then you can use also bigger voltage. Now the electric field will also be increased. Yeah. So this is the way how we employ it according to these equations. E multiplied by voltage divided by R2. So of course the electric field is depending on R1 as well. Okay. So in order to use at the higher voltage and the higher system, then the R1 should be equal to R2 divided by exponent. Yeah. But at the higher voltage 22 kV, the minimum ever electric field will be 11 kV, 11.9 or 12 kV per millimeter at the surface of R1 here, the inner electrodes. So because of this 12 kV per millimeter at voltage of 132 kV, so we cannot use gas because it over 9 kV per millimeter. So one thing that you can do is you might increase the pressure if you want to use gas. If you increase the pressure according to the Paschen's law, so this will be learned on the next chapter and chapter 2, then the electric field may be reduced. Okay, yeah. We can increase the strength of the insulations. Then you can reduce the electric fields. Or if we cannot use gas, then what we can use, we need to use oil. Okay, oil. Yeah, so that's why oil basically we can use at higher voltage lah. Okay, but one disadvantage of the oil, if leaking happen, then the oil will be disappeared, and then what left behind is air, and we know air is very low quality lah. The electric field strength is lower. Alright, okay. So it's already 10 o'clock. Sorry for taking your time. So I think I stop now. Hopefully, actually, I want to finish out the chapter, but I cannot. Yeah, okay. You want to show again the attendance? Okay, can. Where is the... Alright, wait. Yep. Yeah. Session 3 and session 4. Right. Okay. So session 4. Right. Alright. Okay. I think I stop now. Because actually my intention to finish out the